Hey guys, welcome back to Among Icse Insight. So sorry for the delay in the video. I was just editing for the upcoming videos, which is tomorrow and day after tomorrow. I'm gonna do a live stream of whole physics and biology. So I hope you guys are waiting for it. So let's get started with current electricity today. Actually, I said I'll do live stream of nervous system today, but I couldn't because I was busy in editing current electricity, and the upcoming video is which circulatory system. So I'm gonna do two videos today. So let's get ahead and start, guys. First of all, charge is the physical property of matter that causes it to experience force when placed in electromagnetic field. Two types of charge, positive and negative. See, what is a charge? When you place something in a magnetic field or an electric field, it or in electromagnetic field, it experiences it experiences a force. This is a physical property of matter. This experiences a force when placed in electromagnetic field. I think you all know the types of charges, positive and negative charge. Obviously, when two non-conducting bodies are rubbed together, they get charged. See, take a towel, take a iron rod, or I think most of you have did this magic trick called taking your scale, rubbing it in your hairs, and then putting it on a piece of paper, and paper gets attached to it. This is due to charge. Okay. Next, the SI unit of charge is coulomb. Is an Charge is a non-conductor. Like in a non-conductor, charge reside at a point, so there is no flow of electrons. In a conductor, charge can move or flow because they have large number of free electrons. Okay. The unit of charge is 6.25 into 10 to power 18 electrons. It's mine. Yeah. Next, current. It is the rate of flow of charge. I is equals to Q by T. It is measured by ammeter connected in series. The SI unit of current is ampere. 1 I is equals to Q by T. 1 ampere of current is equals to 1 coulomb of charge passed through a conductor in a time period of 1 second. Okay. Potential. The amount of work done per unit charge is known as potential, and this is also like potential is the bringing a test of positive charge means bring the amount of work done in bringing a positive charge from in bringing a positive charge from infinity to some point. Potential is the amount of work done in bringing a positive charge from infinity to some point. Okay, the SI unit of potential is volt. V is equals to W by Q. 1 volt is equals to 1 joule per 1 coulomb. And potential difference, like potential is from infinity to some point, but potential difference is from point 1 to point 2. Okay, just remember this difference. First point minus second point between 2 points is equal to the work done per unit charge in moving a positive test charge from one point to the other point. Okay. Next, if we move ahead, what is Ohm's law? See, Ohm stated a law on resistance. The current flowing in a conductor is directly proportional to the potential difference applied across its ends. This provides the physical conditions and temperature remains constant. See, when the physical temperature and conditions are constant, physical conditions and temperature are constant, the resistance remains same. But if they are different, there is a slight change in physical condition and temperature, the resistance changes. See, if you take a wire of solid metal, like a solid wire, its resistance is different compared to the same wire but in liquid form or in molten form. The current flowing in a conductor is directly proportional to the potential difference applied across its ends. This was Ohm's law. Okay. Conductance, the reciprocal of resistance, the SI unit of ohm. Okay. It is obeyed only when the temperature remains same. Ohm's law is obeyed only when the temperature remains constant. Slope of V versus I graph. A straight line shows ohmic resistors, a curved line shows non-ohmic resistors when you draw a VI graph. Okay. Ohmic resistors, these conductors obey Ohm's law. Non-ohmic, these don't obey Ohm's law. Factors affecting the resistance of a conductor. Material of a conductor affects, length of a conductor also affects. See material. Now if you take a wire of aluminium, the conducting is more in aluminium compared to copper. So sorry, not yeah, in compared to copper. But if you take silver, it has the most conductivity and zero resistivity. Okay, material of a conductor. And length of conductor, resistance is directly proportional to length. When you increase the length, the resistance increases. When you decrease the length, the resistance decreases. Thickness of a conductor, see, thickness of a conductor is inversely proportional to the resistance and directly proportional to the length. Because larger area, when there is a larger area, the current increase, resistivity increases, and where is a smaller area, the resistivity decreases. Okay. Next, temperature of a conductor. Uh, they both are directly proportional. If you increase the temperature, resistivity increases. If you decrease the temperature, resistivity decreases. Okay. Specific resistance or resistivity. It is the resistance of a wire of that material of unit length and unit area of cross section. The unit is ohm. Ohm meter is specific resistivity of a specific length of a wire and of that the area of that specific length, that is called a specific resistivity of a material. Okay. Next, factors affecting resistance: length, area of cross section, specific resistance, as I told you already. Okay. Temperature, see, length increases, resistivity increases, resistance increases, area of cross section increases, resistance decreases, resistance increases, area of cross section decreases. Specific resistance, um, low for metals or alloys, high for insulators. Temperature increases with temperature for metals but decreases with semiconductors. Conductivity, the reciprocal of specific resistance is conductivity. The SI unit is Slemen per meter, S by M. Electric cell, I know I think most of you have seen a cell in your house. You use it for for your TV remotes, AC remote, fan remote. Sometimes even you use it for wall clocks, and not old time wall clocks, not digital ones. Okay. A device in which a constant potential difference is maintained between two terminals by a chemical reaction to get regular flow of charge in a cell. Chemical energy changes into electrical energy. See, there may be a question on this line: what change occurs in cell? Okay, chemical to electrical. Okay. And a device in which constant potential difference is maintained between the two terminals. The positive and negative terminal have a constant potential difference. There is no change in it. This is known as a cell. Okay, electromotive force of a cell, with no current is drawn from a cell. The potential difference between the terminals is called EMF. The EMF is measured in volt by voltmeter, and EMF voltaic cell is 1080. Daniel cell is 1.08 volts. Okay, these are examples: Daniel cell, voltaic cell. Okay, when no current is what is electromotive force? No, when no current is drawn from a cell, the potential difference between the terminals is called EMF. See, now I have not yet connected, like I have connected a cell to something, but the switch is open, so no current is drawn from that cell. So at this moment, the cell is not undergoing any type of reaction. So this is called EMF of a cell, electromotive force of a cell. Internal resistance of a cell. See, each and every wire, thing, whatever you take, which conducts electricity, has its own internal resistance. Okay. Yeah, I'll just wind up this chapter in 2 minutes, guys. I'll not take more than 2 minutes. Okay. Maybe 5 minutes more. Okay. I'll not take more than 15 minutes, guys. Okay. And the resistance offered by the electrolyte inside the cell, it causes voltage drop. See, when the internal resistance always causes the voltage of a cell or any object to go down. See, if you are generating a 240 volt current and there is an internal resistance in that object which is more or less, take it around average something, that makes the 240 volt current to drop down to 220 volts, 210 volts, or even 239 volts something. Okay. V is equals to IR. I think most of you know this. Okay. It's the internal resistance unit is ohm, external resistance unit is ohm. Okay. The factors affecting internal resistance are surface area of electrodes, distance between electrodes, the nature and concentration of electrolyte, the nature and concentration Okay, that's repeated again. Excuse me. If current is drawn from the battery, the current drawn through each resistor is also what's that? Okay, guys, just give me a second. I'll just zoom in and yeah. So if current I is drawn from the battery, the current drawn to each resistor is also I. See, if you take this circuit and take here this battery, so there's some 0.1 ampere current drawn here. So the current passing through all these resistors is also 0.1 ampere. Okay. By Ohm's law, potential difference between A and B is equals to A and B is equals to VA minus V is equals to IR. Okay, and potential difference between B and C is equals to V. This is V1, this is V2, VE minus VC, which is IR2, IR3. On adding, we get V1 plus V2 plus V3 is equals to V1 is equals to VA minus VD. IR1 plus IR2 plus IR3 is equals to I into R1 plus R2 plus R3. IRS, which is series, I into R1 plus R2 plus 3. RS is equals to R1 plus R2 plus R3. See, when you connect some resistors in series, no, the total resistance you can just find out by adding the resistance provided by each resistor. Just now, for example, take a resistor in here. Okay, this resistor is 5 ohm and this is 5 ohm. So if you think these are connected in series, okay, you just think for now they are not, actually they are in parallel. Okay, when these are connected in series, no, the sum of total these two resistors is just 10 ohm. You can just directly add them. But when it comes to series, you have to add in the form of fractions like 1 by r1, 1 by r2, 1 by r3, 1 by r1 plus 1 by r2 plus 1 by r3 plus 1 by r4, so on. Okay, like now this is the battery. There are three resistors here, r1, r2, r3. Now I want the total resistance of these. So what I'll do is take, this is 5 ohm, this is 5 ohm, this is 5 ohm, and let me just tell you a fact, guys. When two resistors like this r1 and r2 are having the same resistance, same amount of resistance, 5 and 5, so you can just take that 2.5 directly, no need to do anything, you can just take it as 2.5. Okay, this both adds up to 2.5, and this one adds 2.5 plus 5, 10 by 25 plus 1 by 5, which is 10 plus 5 by 25, 10 plus 5, 15 by 25, 3 by 5, which is 1.2 something. It's like around 1.2. Okay, so here you will get a total of 1.2 ohm resistance. When they are connected in parallel, you have to do 1 by R1 plus 1 by R2 plus 1 by R3. This is the mistake so many children are doing during exams. So please don't forget this thing. 1 by R1 plus 1 by R2 plus 1 by R3 during what? Parallel. Series R1 plus R2 plus R3 and so on during series. Okay, next if we go ahead to electrical energy. In daily life, electrical energy is converted into different forms. Heat energy: when electric current passes through a heating element, the energy gets converted into heat energy. Light energy: when electric current passes through a bulb filament, it heats up and emits light. A mixture of juicer motors converts electrical energy into mechanical energy with some heat loss. When electric current passes through an electrolyte, a chemical reaction occurs converting electrical energy into chemical energy. Okay, daily electrical changes you see in your household. Okay, you can just check this out. Um, Take a oven or a geyser, you just pass current through it and you will get hot water, or from oven you will get hot items. So that electrical energy is converted into heat energy. And here light: when you pass light to through a bulb or a PO sorry, LED light or a normal lights, any lights in your house, they give up like that electricity is converted into light energy and give light. And in old time bulbs, there was even heat energy emitted because the bulbs would heat up. Obviously there was glass. Okay, a mixture of juicer motor converts electrical energy into mechanical energy with some heat loss. Okay, and chemical energy, when electric current passes through electrolyte, a chemical reaction occurs. I think you will learn this in electrolysis. I'll just do a video of that chapter very soon. I'm planning it. Okay, measurement of electrical energy. Let current I flow through a conductor of resistance R for time t when a voltage V is applied across its ends. Electric power and its expression. Power is the rate at which electrical energy is supplied by a source. Okay, um, P is equals to energy supplied by time within time t. P is equals to W by T. Okay, W is the energy supplied, and T is the time. Since Q is equals to IT, P is equals to QVT, which is equals to VIP, which is equals to QV by T. VIP is equals to T into Q by V, VI. Okay, I think you guys understood. If not, I'll send this notes. You can just recheck there. By Ohm's law, I is equals to R by V. Okay, R into V, sorry. The SI unit of power is watt. 1 watt, the power consumed by 1 ampere of current flows through a circuit of 1 volt of potential difference. Larger units 1 kilowatt. This is used in your houses. Go open your, like, I don't know where you're sitting, just go out of your house. There will be a connection box or any like a meter box, and you open it. But be careful with items like those are electricity items. Be careful, open it, and there is a meter reading your usage of current, and you watch it for some time. Like you will see a number beside it, you will see kWh, kilowatt per hour. That's the commercial unit of electrical energy. It's given here. See, 1 kilowatt hour is equals to 3.6 into 10 to power 6 joules. See, when in your house, if you use 1 kilowatt hour, you're using around 30 yeah, 3 crores 60 lakhs, around something 36 crores. I don't remember exactly. Wait, let me calculate. Yeah, it's 36 lakh joules. You are using 36 lakh joules if you are using 1 kilowatt per hour. Okay, 1 megawatt is equals to 10 to power 6 watts. 1 gigawatt is equals to 10 to power 9 watts. SI unit of energy is joule, and power, yeah, I said you just now. Definition of 1 kilowatt. The kilowatt is the energy consumed by a 1 kilowatt electrical appliance running for 1 hour. Power rating of common electric appliances is 100 watt, which is 220 volts. It means that it is, if the appliance is connected to a 220 volt supply, it consumes 100 watt of power. Resistance, from this rating we can calculate the resistance of the appliance, safe limit of the current flow, etc. And P is equals to V square RP. Okay, energy calculations in homes. I think most of you know how cost of electricity or energy is calculated in your houses. And I think that's it for today, guys. Thank you for watching. Bye bye. See you again in the next circulatory system video, which I'm gonna upload around 6 p.m. today. See you there. Bye bye.